Hey guys, my name is Blake and I have a really cool video for you guys today. Do you ever wonder how barrels are designed, or muzzle brakes, compensators, gas blocks, tubes, bolt carrier groups, suppressors, everything? It's designed by a little bit of engineering, so this might be a little dry for some of you, but I want to show you guys because I think it's one of the coolest things, how you can calculate everything based off of chamber pressure. So let's dive into it. So what I have in front of us is going to be some props. I have a barrel here with the gas tube attached. In today's video I'm going to be talking basically about the firearm basics and how things generally work so that we can get a general understanding of how I'm going to use 20,000 and 55,000 chamber pressures to calculate a lot of my variables throughout this process. So I hope you guys can follow along. It's going to be a multiple part video or series, so this video is basically just the intro. So let's dive into it. The props here on the front, it's going to be, I have a barreled upper with just a bolt. These are just some dummy rounds and some bullets, some calipers, and then I have some sheets here that'll help me explain everything. And this is just a mag here. So the first part that we're going to get into is, how does a cartridge work? A cartridge works off of a detonator or an ignition source that's called a primer. And the primer is hit by a firing pin, or you could think of it as a nail. And when this happens, the gunpowder in here is going to expand at an extremely fast rate and turn into gas. Instead of it being gunpowder like that granular mixture, it's going to turn then into gas. And what that does is it pushes the bullet down the barrel. And this is just some rifling to stabilize the bullet. So that's the first page. Let's keep going. So everything is going to be about pressure. I'm going to be using, let's see, sorry about that, 300 blackout for an example, so it's easier to visualize. What we're going to do throughout this is we're going to act like this is a sealed surface. So if you were to just take one of these and then cut the bullet right off there and pretend the bullet just sits right there, now this is a little soda can, and we're going to take that pressure of 20,000 or 55,000 and we're going to calculate the pressures throughout. And those pressures are important because it can give us a lot of information on what the pressure is going into the gas tube at that distance from the chamber. Going back into the bolt carrier group, we can calculate a lot of things. So this is kind of going to say, what can we answer knowing a 20,000 and a 55,000 pressure? So what's the pressure at the muzzle? That's important for calculating things like muzzle brakes or compensators. This is a dual one, because the gas pressure coming out of these ports here is going to create forces that's going to help make the firearm more stable, or barrel more stable when it fires. So we're going to call this pressure at the muzzle the uncorking pressure. So you can think of it right where, there's a cork that's traveling down at each of those points. It stops, and we're going to take a still frame of that and use that pressure there. So we can then find the pressure at the gas block like I talked about, if it's going back through the gas tube. How a firearm works, I should say in the beginning, is this is a dummy round. What will happen is it'll go in through here, and this bolt carrier will slide up, pick the round up, and push it into the chamber right here. It'll then fire through the bottom part of the gun that's not here, and then once it gets through here, it'll pick up some of the pressure from, or gas, I should say, and the gas will travel down this barrel and into this tube, and we can just picture it cycling. So this is the last we'll probably see of this prop here. So I'm just going to put the bolt in the back. So it would pick it up like this, and then it would push it in off of that into the chamber, and then fire it and pull it back out. So on to the next. Try and go through this as fast as I can. I know I can get a little carried away. So after we know what the pressure then is at the gas block, now that you can kind of know what the gas block is, we can calculate that acting like an orifice, and through fluid dynamics act like this is just a restricted tube, and see the pressure back here at the bolt carrier group. And that'll also give us, an understanding of how much pressure is there, which is actually experienced on the carrier through the recoil spring. And the recoil spring will then tell us, because we know how strong the recoil spring is, the friction, the slip, and a lot of that acting on the bolt carrier. So this is kind of what I was talking about earlier. When you're going into barrels and how thick they need to be, yeah, you can make it extremely thick, but you could also have it be pretty thin. And so this is just a demonstration of showing you a thin barrel with a suppressor, and then a thick barrel. So does it really need to be this thick? And we can calculate how thick it needs to be, because you can think of it as the pressure is really big up here at the chamber on both of these, but it slowly decreases as the gas gets more volume to expand and the bullet travels down the barrel. So what actually will happen is barrel manufacturers will taper the thickness of the barrel as it gets closer and closer to the muzzle. And then also here you can kind of see we have, let's say, a suppressor, and on that suppressor we're going to have that certain pressure called that uncorking pressure here, and we can reduce that uncorking pressure to a volume or sound level that makes it so quiet that it's okay. I'll explain that on the next page. So the pressures in the beginning, I keep saying pressure, I'll try to stop, but right here is going to be called the hoop stress. And that's one way to calculate these forces that are going to be pushing out along this tube based off of that initial chamber pressure. Okay, so what we were talking about earlier is, yeah, we can make it extremely thick, but what if we want to also worry about sound? What makes a gun or a sound so loud? There's basically one thing that makes a sound loud, and that's the sonic crack. But it comes from two things. It can come from the bullet sonic crack, which means the bullet's going faster than the speed of sound, and that's going to create a sonic boom right as we hear it. And then the next thing is going to be the expanding gases creates a sonic boom. The reason for that is because if you can think about the gunpowder pushing a bullet here, so then we have the gunpowder is expanding and pushing this down the barrel. If this is going faster than the speed of sound, then obviously the gas is going to be expanding faster than the speed of sound, because that's what's imparting the energy on the bullet. And so we can limit the speed of the bullet to be slower than the speed of sound, but we can't limit the gases, or can we, to being slower than the speed of sound. So it's going to be from the expansion of the gases. So here's another diagram. You're going to have a lot of these. The expanding gases and the pressure is on, you could think of this, the y-axis, and on the x-axis is going to be the barrel length. Initially, when the primer is ignited, this is just a rough diagram, it's not this smooth. The pressure is going to spike, and as the bullet starts to slowly move, the pressure is going to drop as the bullet slowly moves down the barrel. The next one is going to be about the velocity of the bullet, and you could think of this as also the barrel length on the x-axis, and that's on the y-axis. The max velocity is going to be achieved at the muzzle because there's no more gases pushing it. This is just going to be a diagram then of what I was talking about. So the diagram is just showing you how sound waves and pressure waves are created by the compressed air forces that we're talking about, and that's what you're going to hear is a sonic boom. So these compressed air is going to translate into your eardrum, and that's what you're going to hear. So that's either by the bullet or by these rapidly expanding gases coming out of the barrel. So we can do something interesting here with this graph. I was going to show you as another pressure versus barrel length. We've already shown you this one as it slowly goes down. But what would happen if we extended the barrel or gave it a large area to expand in a confined space like a suppressor? And so the pressure will dramatically drop down to an area or to a level to where those expanding gases aren't going faster than the speed of sound when they escape the final end of the muzzle, which would then be the suppressor. So we can talk about that in terms of suppressor length and size. And this would then be the gas block where we could calculate the, what this is at that point. You can also change the gas port position based off of different chamber pressures. And some of them are going to be this short, some of them are going to be out here, here, and those lengths are called pistol, carbine, mid-length, and full-length rifle. Down here at the very end is when we get into how I'm going to be modeling things. It's going to be cylinders. These are just side cutaways. It just easier for us to visualize with that 300 blackout like I was talking about. This is going to be the soda can. Hey, buddy. Anyways, so if we were to cut this off and act like that's, soda can, we're going to take that and visualize that then as a cylinder, and the barrel is a cylinder. We can also do that with suppressor as a cylinder, barrel as a cylinder, and the chamber is a cylinder. There's two ways that we can calculate the variables throughout it. One of them that I thought through calculus or without calculus. I think it'd be easier that we do it without calculus so that we can follow along. And I'm not that good either at it, so I can make a lot of mistakes. So even if I make a lot of mistakes here, feel free to correct me. Here I'm going to have the inert gas law, which is going to be pressure times velocity is equal to the number of moles times the universal gas constant times the temperature. The only thing with this is, yeah, we know the initial chamber pressure and we know the initial chamber volume. We can calculate that based off of, let's just use this cartridge as the chamber. And then we're going to not know the number of moles that's in there, but we can then know the universal gas constant, and the temperature is questionable because I think it's a changing temperature as the volume also changes. So I think it'll be a little hard for us to calculate. The other one that we can use is going to be just a pressure force equation, which is going to be the force in pounds over the area in square inches. Pounds per square inch, PSI, that's how you get that. So we're going to actually have a change in pressure because the volume is going to be changing. So the area is going to be changing, but the same force. So the force is going to stay constant because there's a finite amount of gunpowder in one of these, and so there isn't going to be any there is no more energy added after the initial energy. So we're going to treat that as a closed system. And this is just kind of some of the calculus that you'd kind of see is that you can have a changing volume throughout it or changing area, and it's a lot easier to calculate this based off of using an integral or something like that, but it's just easier to follow, and I'm not that good at it, to be honest. So you can see that this isn't just a straight cylinder. They actually reduce the area as it goes along. Even though the center of this is all 0.3 inches, let's say, the outside of this, thickness-wise, is thicker here because there's more pressure here, and then it slowly gets smaller. You can see that as it goes towards the muzzle. And that's going to be pretty much it for this video. I'm going to get into give-ins in this next one, so I hope you guys followed it, and if I make any mistakes, again, feel free to correct me down below.